Okay, welcome everyone. Welcome to Geomatics seminar. Today we have a Dr. Craig Glennie from University of Houston who's going to give us a seminar. And Dr. Glennie, he is a professor in civil and environment engineering at the University of Houston. And he is also principal investigator of the very famous program NCOM, which is a National Science Foundation funded National Center for Airborne and Laser Mapping. And I know that some of you guys and the graduate student, we've been using some of the Lidar data sets, or also in hyperspectral data set that's been collected by this NCOM Center as well. And Dr. Glennie, he has some industry experience before he joined University of Houston. So he was a vice president of engineering for TerraPoint, which is a lidar remote sensing company with an office in Canada and United States. And he's active in design and development and operation of kinematic remote sensing system for more than 20 years. And Dr. Glennie holds a bachelor and PhD degree in geomatics engineering, both from University of Calgary in Canada. And I have some personal connection with Dr. Glennie because I remember those days when I actually went for the interview for University of Houston in 2011. That's when I first met him. And I'm really glad to have Dr. Glennie back into our geomatics seminar series. And thank you very much for finding time to visit us to give a seminar. And with that, please take it away.
Thank you very much. Well, thanks for that nice introduction, Jinha, and everybody else. Nice to virtually meet you. I'm excited to be here over Zoom for the next 45 minutes or so to talk to you a little bit about one particular component of my research. So as Jinha said, my background is in geomatics, but I'm going to present something that uses some geomatics tools, but is really motivated more by an earth science question. And that earth science question is, how do we look at earthquake or fault deformation in something called the near field? And basically what that means is in the zone very near to where the fault rupture actually happens. And so we're going to look at using mobile laser scanning to get down to kind of sub-centimeter level distributed fault creep in those areas. This work has been going on for almost 10 years now between NCOM and the US Geological Survey. And so you see there my two co-authors, Ben Brooks and Todd Erickson from the USGS, both geophysicists. And then, although I'm presenting this work, the bulk of the heavy lifting has been done by my PhD student, Sean Zhu, who's actually, will be defending his PhD next week, as a matter of fact, on this material. So just to give you a little bit of background on the National Center. So the National Center for Airborne Laser Mapping is an NSF-supported facility. Supported to supply on-demand data acquisition. And we have been in operation since 2003. We're currently funded to the end of next year. The Field Operations Center is based out of the University of Houston, but we do operate in partnership with UC Berkeley. They provide some of the earth science help for us. Our focus is in kind of 5 areas: data fusion, sensor development, and sensor characterization. Today, I'm really going to focus on talking about the last 2 here, the algorithm development and engineering and science applications of Lidar data. So, as I said, we're a field instrumentation site, which means that we collect data from a number of different platforms. We started out primarily as Lidar, but we now also have hyperspectral imaging sensors. We also do airborne synthetic aperture radar. We do Lidar from large aircrafts. This one's actually in Antarctica. Helicopter-based platforms, mobile laser scanning, backpack mounted, UAV, basically any device that it's useful to put a laser and a camera on with a GPS INS. We're kind of interested in the data sets that come out of those. That has turned itself into a lot of projects. So over the last 10 years, we've done somewhere north of 300 projects, working for 225 different PIs at 110 different universities, not only in the US, but throughout the world. And, you know, we like to say that we will go anywhere, and we have gone everywhere from Alaska to Antarctica to collect data, and a lot of places in between. Important thing here is these are research projects only. We're not flying around doing, you know, FEMA floodplain mapping or things like that. These are primarily earth science and archaeological projects where there is a research component to it. So normally funding coming from an agency like NASA or NSF, for example. In terms of metrics, how NSF measures us is what our impact is. And so, you know, Jinha will be aware of this because he's got to track his citations and publications and what have you. So this is kind of the publication record for projects using NCOM data. Right now, there's approximately 900 publications that have used NCOM data, and they have approximately 16,000 citations. So if NCOM was a person, I think they'd probably be granted tenure at most universities based on those results. A couple of just quick examples of projects. I don't want to go into too much detail here, but this is, you know, we were primarily started as an earth science center, and this really gives you an example of one of the really key uses of LIDAR for earth sciences. So on the left here, this is along the Flathead River in Montana, and that's the full point cloud. And you can see a lot of vegetation on top, hard to see what's on the ground underneath. On the right here, this is that same scene with the vegetation removed using the LIDAR. And you can see, of course, there's this massive landslide underneath. And, you know, it was kind of initially images like this that really sold NSF on the need for a center like NCOM to collect data for earth science applications. In recent years, we've actually been doing a lot more projects in the area of archaeological prospecting. So this is a first return image, LIDAR image of an area in Belize called Caracol. And if you look closely, you can see up here, there's actually a pyramid structure and some other buildings. Obviously, those sites were known, but the rest of the site is covered in very thick vegetation. And this is one of the things that has made LIDAR very valuable for archaeological prospecting, is when you take that vegetation away, suddenly you see just how massive that site actually is. These ripples on the hill here are actually terraces from farming in the area, and they give the archaeologists an idea of the size of the site. The other interesting thing is you can see the main road into the site here, and you can see another, looks like a road. This is actually an ancient causeway leading out of the site. The researchers knew about this causeway, but they actually, in the LIDAR data, we discovered another causeway leading out to the site here. They didn't know where that goes. Well, it turns out 3 years later, we came back with to do another LIDAR survey, and we found a previously unknown Maya site at the end of this causeway about 10 miles away. So recent years, we used to do 90% of our work for earth science, and now it's probably 50-50 earth science and archaeology. So that's just a little bit quick background on the center itself. Now I just want to jump back into my talk here on looking at surface displacements in the near field. And, you know, we want to make very precise near field measurements, but there has to be a reason, a science reason why you need to make those measurements. So I'm going to start off with why the USGS was so interested in this near field geodesy question. And I'm going to start it with a couple of pictures here. And these pictures, A, B, C, and D, are from 4 different earthquakes, fairly similar size in terms of magnitude, but you'll notice some very striking differences between them. The Darfield earthquake in New Zealand here, the area of deformation on the surface is almost 50 meters wide. If we look at the Kumamoto earthquake in Japan, the earthquake deformation is actually constrained to a zone only 1 meter wide. And maybe even more telling, if we look at these two earthquakes, and these are both on the San Andreas Fault in California, just in two different locations. In the Imperial Valley, we have a canal, and you can see that the wall wasn't broken, it was just bent. Meanwhile, if we look further up the San Andreas in California, the 1906 earthquake, when it happened, it actually just sheared everything along that zone. So the zone of accommodation, or where the earthquake happened, was very thin. And the problem is, from a earthquaking or a near fault or shallow physics, is that we have no idea why some earthquakes have this large zone of accommodation and why some of them are small. And more importantly, we have no predictive power on this. Just by looking at the soil or the earthquake itself, or the fault line itself, we can't tell what type of surface break is going to be there. And this is really important because this is happening in the upper, couple hundred meters at the surface where all of our infrastructure is. And so, to look at the Imperial Valley versus San Francisco, from an engineering perspective, if you have this kind of shorter or longer accommodation zone, you can build a flexible pipeline that will, in the case of an earthquake, probably bend but not break. But if you have this type of shearing when the earthquake happens, it doesn't matter what you do for your pipeline design, that's probably going to break. And so it's really important in terms of measuring hazard for an earthquake event is understanding how this width of energy accommodation occurs. The problem is that we really, up until now, haven't had the measurements to try to figure out what is going on. The width of this zone of accommodation is governed by what happens at depth below the earth. And obviously we can't, dig a hole down 10 or 12 kilometers to look at where the fault planes are sitting along each other. All we can do is look at the measurements on the surface and try to invert them to figure out what is going on below the surface. And in geodesy, we would call this an improperly posed problem. It's like measuring gravity from a satellite platform and then trying to downward continue it to the surface of the earth. You're going to amplify your noise, and you're going to have some very large nonlinearity. So you have to be careful on how you do that. So it turns out that what we really need to be able to do is understand what is happening at a depth of, in most cases, kind of 2 to 15 or 20 kilometers below the surface. And I'm not going to go too much into these two figures, but the one takeaway I want you to get from this figure is that here I am showing two different profiles of slip along the fault. So the solid line here shows slip that stops maybe 5 kilometers deep, or is at maximum at 5 kilometers deep, and then starts to tend back towards zero as it goes closer to the surface. The second, the dotted line, shows a maximum fault at about 10 kilometers deep, but then that breaks all the way to the surface. So if you can look at these two profiles, the break all the way to the surface, that would be like the San Francisco earthquake where we had that pipe that sheared. The second one would be more like the Imperial Valley earthquake. Well, if we look at displacement along the earth in distance away from the fault line, you can see that when we get maybe more than about 10 kilometers away from the fault, the displacement profile of those two curves look exactly the same. Geodesists or earthquake geodesists like to use GPS to look at displacement. Well, even though California has very tightly spaced GPS receivers, best spacing even along the San Andreas is maybe at 15-kilometer fault separation. And so you actually, at that distance, can't tell the difference between these two fault profiles. If you want to understand what's really happening below the Earth, you need to be able to measure the difference in these curvatures very close to the fault. And what that requires is very precise measurements of that displacement so that you can actually estimate this curvature to infer what is actually happening below the ground. And so this is really the motivation for our problem. We want very precise measurements very close to the fault so that we can look at this curvature and try to infer what is happening underneath the ground. Problem is, measurements for what's happening at the surface along the fault line are kind of rudimentary. This picture and this profile is actually from 1908 after the San Francisco earthquake. And so what these guys did is they went out and they found features along the fault line that used to be together before the earthquake. And then they measured the distance along the fault and said, okay, well, it's moved 10 meters here. But that's right on the fault. They didn't have any measurements off the fault anywhere else. So this is in a paper in 1908. You would figure in the next 100 years, we probably came up with a better way to do this. Well, these two photos here are showing the exact same thing. This is from the Napa Valley earthquake in 2014, and this is from the Kumamoto Japanese earthquake in 2016. 100 years later, and we're still going out and measuring this with a tape measure. Well, what it doesn't tell us is what is happening near to the fault. So if we have slip that doesn't quite reach the surface, we have this kind of off-fault deformation or this zone of accommodation. So you can see like the fence in my cartoon here kind of takes on this curvature pattern. But if we look at an area where the slip made it all the way to the surface, then you have this straight break and there's no curvature, there's just an offset. And we want to be able to, in both of these cases, if we measured the offset of the fence, we would get the same number. But obviously the physics of the earthquake between these two cases is completely different. And that's really what we want to get at, is that difference so that we can measure or try to model that anelastic deformation that we are seeing in that case A. That's really what we're interested in here. So how do we measure this near field displacement? Well, unfortunately, the tape measure is not going to cut it. What we would like is a method that gives us more distributed, high resolution and high accuracy measurements. One of the primary tools that these engineering geophysicists or these earthquake geophysicists are now using is INSAR. And so this is an example of UAVSAR measurements. So UAVSAR is an INSAR, airborne INSAR flown by NASA out of the Jet Propulsion Laboratory. And this is along the Hayward fault, which runs parallel to the San Andreas fault, but on the other side of the bay. So instead of running through San Francisco, the Hayward fault actually runs through Oakland. And it is an interesting fault in the sense that it is creeping, which means that it is moving at a small rate, a couple of centimeters a year, every year. Well, because it's moving so slowly, when we use a synthetic aperture radar, that motion can be captured by repeat passes, differential INSAR, and you can actually get a profile of that creep. In this case, you can probably get a fairly decent measurement of the near field deformation. The problem is when we have a larger earthquake, and for an example here, I'm going to look at, this is the South Napa Valley earthquake. So this was a magnitude 6 earthquake in 2014. My scale bar is not showing up, but from the north side to the south side of the rupture here is about 10 kilometers to give you an idea of scale. The red lines here are the fault lines along which the earthquake ruptured. Magnitude 6 is not a very big earthquake. Maximum motion or displacement on the ground was about 40 centimeters. To give you an idea of larger earthquakes, magnitude 7, you usually get somewhere between 1 to 5 meters of displacement. So this is kind of a small earthquake by standards, but even though the displacement of that was not very large, when you look at INSAR observations, and this is using Cosmos SkyMed, what you can see is you get hardly any measurements close to the fault. And this is because your INSAR tends to decorrelate, both because of the motion and because of changes in vegetation. In this case, along, Napa Valley is famous for its wine, and there's lots of vineyards and vegetation along the fault line here. So in an actual earthquake event, we're really not able to get those near field observations that we would like. For perspective, GPS locations in this site, there was one up here in the top right, one down here, actually close to the fault, and one off the map over on the left here. So you can see, even though we have lots of GPS in California, it's not nearly enough to help us measure this near field deformation. So INSAR is potentially a tool, but it has problems when you have large ground motion. And so the next thing you'd like to say is, well, can we use airborne LiDAR point clouds, or can we use image correlation techniques to do these type of measurements? And so with the South Napa earthquake, there was actually a absolutely wonderful first case study of this, because just by dumb luck, about 2 months before the earthquake, the city of Napa contracted to have a high-resolution LiDAR data set and 10-centimeter orthophotography collected for the entire county. Just, the earthquake happened on August 7th. We were contracted by Usgs to come along and collect post-event data about a month after the earthquake. And so now we have a high-resolution data set right before and right after the earthquake, both imagery and LiDAR. So this is a wonderful test to see, okay, what can we do with airborne imagery and LiDAR in terms of looking at near-field deformation? And by the way, if you're interested, these data sets are all freely available on Open Topography. So first thing to do is, okay, well, let's forget about LiDAR for a second. Let's look at the imagery. So we have 5-centimeter ortho after and 10-centimeter ortho before. And so the first thing we look at is, can we use kind of image correlation techniques? So CosiCore is a frequency domain image correlation technique. You could use something like, matching SIFT features before and after would kind of give you similar results. But what you see is, even though these images were only about 3 months apart, we had significant changes in vegetation that actually caused a lot of artifacts in the data set, and I've circled a few here. This is actually a big vineyard that you're looking at here. So in June, the leaves were nice and healthy, and by September, they had actually started to die off because you're getting into the dry season. Overall, we were able to measure the earthquake deformation with somewhere around 15-centimeter accuracy with this technique. Next thing you want to do is, okay, well, let's, instead of just using the images themselves, let's use structure for motion, multi-view stereo, and let's create point clouds from this. And then we can use a method like the iterative closest point, for example, to measure change. What happens here, and the SFM in this case was done, I believe, using context capture. We get rid of the noise due to the vineyards because we're able to filter and actually do a ground and above ground. But you still have problems in areas in trees, which is why you see all this kind of speckled noise here. It does a little bit better, but you're still at kind of maybe 10-centimeter accuracy. Next step then is, okay, well, let's just, instead of using the imagery, let's go to the ALS. And the advantage of the ALS, of course, is you have multiple returns, and so you can get through the vegetation and actually get to the ground. And so we're able to then just use a ground model, get rid of any of the vegetation effects. And when we do ICP on that, we're able to get down to approximately 5-centimeter accuracy in terms of measuring the earthquake displacement. How do we determine that 15, 10, and 5-centimeter accuracy? Well, we had to go back to what the USGS was actually doing to measure offsets in that case, going out with a tape measure and measuring things. And so when I give you those numbers, that is in comparison to the field measurements that the USGS made. So it's still probably not the most reliable reference because in this earthquake case, there was significant off-fault deformation, but we don't have any other truth. So it's at least a figure of merit. And we were, I'll be honest, this was published in a paper in 2018 by Ektari and I. Actually, Nima got his master's degree from Purdue about 10 years ago. So a Purdue connection there as well. Fairly accurate with the ALS ICP at about 5 centimeters, but in talking to the earthquake modelers, if they want to be able to measure that curvature, 5 centimeters just isn't going to cut it. They need better observations than that. And so we were kind of after 2018 here sitting with the question, well, how are we going to do that? And so this was really where Sean's PhD work kind of starts, is with that question. Okay, we can get 5 centimeters from ALS ICP. How do we get better than that? And the answer that comes out of that is we kind of borrowed something from in the INSAR world. When they are tracking deformation across time, they use a technique called the persistent scatterer. So they're looking at features that they can track rather than just looking at tracking motion. And so the idea is here, well, can we do the same thing with Lidar? Can we constrain the geometry of the point cloud using known features? And the easiest features are just simple geometry. And the reason we want to use simple geometry is because we can do things like train machine learning algorithms or consensus estimate algorithms to find plane cylinders, linear features in the Lidar point cloud automatically. And then we can use those constraints, the geometric constraints, in some sort of least squares solution to hopefully improve our rigid body estimation of deformation. And so that was really the 3 lines that were the motivation for Sean's dissertation work. So first paper that came out of his work here, this is the looking at mobile laser scanning for the South Napa earthquake. And here he used some cylindrical primitives to track fence posts. And he detected those fence posts automatically using a deep neural network that he developed. And this was kind of a first proof of concept to see how much more accurate can we be if we model both the geometric primitive and the rigid deformation at the same time. So the approach is kind of summarized here. If we consider knowns and unknowns in both Euclidean and feature space, our knowns are of course our Lidar point observations. In feature space, our knowns are the geometric form of the primitive, so cylinder, plane, etc. And what we really want to estimate, the unknowns, are the ground displacement and the parameters of the primitive. If we go back to using just straight ICP, we're really not taking advantage of anything in the feature space. We're only staying in the Euclidean space. We're taking the Lidar and we're trying to directly get the ground displacement. What we really wanted to do is the second strategy, and that is take the point cloud, extract the primitives, model them, and then use that modeling of the primitives to then estimate the ground displacement. And so we're encompassing the modeling of the primitives into it. Functionally, this still all happens in one step, but there's more pieces to that puzzle. So why does that strategy work a little bit better? Well, before we went there, we wanted to make sure that it actually would work. And so we just did some simple tests. 2 point clouds of a sphere here. We apply a synthetic transformation between the 2 of them. And then we do a couple of things. ICP point to point, ICP point to plane, and then a model based. And if you look at the statistics here, what really comes out at the end is when we're using the model based, we get a factor of 2 or better at some point constraint on it. And try to kind of explain it with this cartoon up here. If we have 2 point clouds, the gray and the darker gray, when we're doing point to point distances, we're still encompassing all of the noise of the Lidar observations into that distance. If we look at point to plane or point to model, what we're doing in that case is we're maybe fitting a plane through one data set, but then we're encompassing all of the point noise on the other side into it. But if we use model to model, we're reducing the noise of the model by averaging over the surface, right? So if you have 1,000 observations of the plane, your best fit plane is going to be a better representation than any individual point. And so that's really the motivation behind it. And based on this, we were fairly confident it's going to work, but we want to go and actually test this on a real data set. And so unfortunately, along the South Napa earthquake, we did not have mobile laser scanning before the earthquake. All we had was laser scanning afterwards. Now, one of the things I didn't know about earthquake faults before I started studying them was they are not deterministic events. When an earthquake happens, all of the motion doesn't happen instantaneously. You have an initial motion, and then usually for sometimes months or even years afterwards, the ground continues to relax at a slower rate, kind of like an exponential decay, until it stops. And so what we did in South Napa was right after the earthquake, we collected an MLS survey, and then we came back about a month later and did the exact same route with that MLS again. We were estimating in some areas we would see maybe 5 or 6 centimeters of motion in between the two MLS surveys. What we were using was basically a couple of terrestrial scanners, a VZ400 and a VZ1000, mounted on the back of a truck with a high-end GPS INS. And you can kind of see in the picture here, most of this area along here is covered in vineyards. And when we looked at the scans of the vineyards, I think when you look at it almost immediately, you can see that every one of these vine rows has a whole bunch of posts in it. And the posts are there to hold the vines up. And they also make wonderful reference markers, which is why we decided in this first study to look at cylindrical primitives, because there was an abundant number of them in all of these vine rows. So the first model was to take these two MLS data sets, one collected 7 days after the earthquake and one after 34. And then we trained a machine learning algorithm based on the PointNet description to extract the cylindrical primitives from them and used a ransack method to model them through a simultaneous with the displacement through a least squares adjustment. And so we are getting both deformation and a model of the primitives all in one step. We are then comparing those to ground measurements of the displacement over that 27-day period. So looking at the results here, this is just, sorry, I forgot about this slide. This is just showing a little bit of the machine learning classification. So obviously, Sean didn't want to have to go through this data set and individually delineate each one of these posts. So he trained basically using a few of the tiles, and then he used that to train a PointNet model to go in and automatically extract that. And the next slide here kind of shows that automatic extraction. So he divided his machine learning into posts, vegetation, guide wires, and ground. And so on the next slide here, I'll kind of show a maybe 3D model of, so we start with just the posts that were extracted from the machine learning, then the vegetation, and then the guide wires and ground wires, and then the ground underneath. So that worked quite well, and it allowed us to automatically extract thousands of cylindrical primitives that we could then use for modeling. And so when we did that, we get a whole bunch of primitives here, and there's this figure's kind of busy, but what I want you to just kind of focus on is the results on the bottom here. And so when we looked at differences across in motion of posts across the fault line, we came out with differences that were on the order of about 4 centimeters. and that was distributed up and down the fault. When we compared it to the actual measurements made by the USGS using total station and theodolites, their accumulated motion over that same period was at the level of 4.39 centimeters. So initial was a nice result that showed us that, hey, we can probably improve our accuracy by using these geometric constraints. The unfortunate thing with this study is that not very often are you going to get an earthquake that has a whole bunch of fence posts all over the fault line. And so while it was a nice result, it's practically, you're probably not going to be able to use it in every earthquake. And so the next step was, can we take those conclusions that the geometric primitives are efficient to track deformation at a kind of centimeter level accuracy? Can we take that and look at other primitives that may be more widespread to improve the usability of the methodology? And so that kind of leads to the second paper. In this paper, rather than looking at an earthquake, we're going back to the Hayward fault, where we were measuring aseismic fault creep. So this is the fault that goes through Oakland, that's kind of creeping at a rate of about 2 centimeters a year. With the USGS, we've been doing mobile laser scanning over that fault line once a year, every year since 2013. So we're actually at our, well, it would be our 9th, if not for COVID. We actually missed a year, so it would be our 8th observation this year. So what second step here is that, that this fault is in a more urban area, and so we thought, well, can we use, rather than cylinders, simple planar primitives? And we want to then look at an even smaller motion. So here we're talking from 2015 to 2017, maybe a couple of centimeters of motion. Can we actually detect something at that level? And so this just gives you an example of what we were looking at. We have mobile laser scanning. So on the left here is the 2015 data. On the right is the 2017. And you notice the point clouds don't quite look the same. We have some occlusions due to differences in vegetation or parked cars or different viewing angles, etc. But what we want to be able to do here is automatically extract planes from the figure on the left, automatically extract planes from the figure on the right, match those planes together, and then be able to use that matching to estimate how much the fault line has moved in the intervening 2 years. And so, just jump ahead a little bit here. What we looked at is a combined least squares adjustment model where our inputs are really just the point cloud coordinates and the planar ID, and our unknowns are the rigid body transformation parameters and the normal vector of the plane, the equation of the plane, etc. And so we are going to take those and put them into a combined least squares adjustment with the constraint that the equation of the plane should hold. And so when we do that, what we're really doing in the adjustment is we're taking, if we consider the red to be the after planes and the blue to be before, we're adjusting them such that the two planar surfaces will move together and minimize the difference between the two of them. And that minimization will tell us what the rigid body transformation is. And really this approach is kind of stealing from a fairly old boresight approach that was developed by Jan Skalud at EPFL and Derek Lichty at the University of Calgary, where they used planar surfaces, but in their case, they used it to determine the boresight calibration parameters for an airborne LiDAR system. Here, we're just changing it to look at measuring the deformation due to the earthquake. One of the things that comes out of this is we need to be very careful about the planar geometry, because we are only sensitive for a single plane. It is only sensitive to deformation in the direction of its normal vector. And so if we want to determine 3D distributed deformation, we need a range of normal vectors such that we have strength in all three directions, X, Y, and Z. And so very early on, we realized that we needed a measure when we were doing this solution to measure the strength of our geometry. And where we go from there is back to the idea of GPS. I'm sure everybody with GPS is familiar with the idea of PDOP. And PDOP is nothing but the trace of your covariance matrix to look at the strength of your solution in the X, Y, and Z. We can do the exact same thing for our situation, just replacing our satellites with our planar normals. And we can use a measure of the strength of those planar normals to tell us how robust our regression is going to be. It really allows us to automatically determine whether we have weak, strong, or stronger geometry. What that allows us to do then is decide, okay, well, how many planar surfaces do we need in an area in order to reliably estimate our deformation down to the level of accuracy that we want? And so, let's jump through these a little bit here. First study we look at is, okay, well, let's measure this PDOP versus the number of planes that we have. And looking at the study here, we kind of somewhere between 10 and 15 planes, we get to a point of diminishing returns. And so that kind of sets your minimum grid size for your search in an urban environment. Okay, well, I need to have 10 or 12 planes before I'm good with the solution. So, that probably corresponds to maybe a search area of about 10 square meters, for example. So using that PDOP, we are able to estimate for each one of the planes a deformation vector. And just to highlight here, I've colored these by low PDOP versus high. And you'll notice all of the red arrows are kind of a little bit of outliers. And so we also used a map like this to say, okay, this is a good way to get rid of outliers and make sure that we actually have a nice, strong solution. In this area along the Hayward fault, so again, this is the San Andreas fault, kind of runs through San Francisco. This is the Hayward fault that runs right down through Oakland and actually right through the UC Berkeley campus as well. The USGS has been monitoring the Hayward fault since the 70s. They have these stations set up along the fault where they basically go out once a year and they measure with a theodolite deflection angles. And they are able to determine from those deflection angles, because they're using a 1 second theodolite, down to the kind of millimeter level with some good observational techniques. So we have some really good ground truth along here on fault parallel displacement or creep along this. And so this is a good study area. Our study area where we have MLS data is kind of this white square. And this was chosen because there's a lot of houses in there. So we have a lot of planar surfaces or urban markers that we can use to track displacement. So when we look at that, we actually come up with this kind of distributed deformation map on the left here. So we have the kind of fault line would be running through here, and we have our relative displacement across the fault of a couple of centimeters. And you can see the measurements are fairly consistent. There's some variation in some areas, but overall, results are kind of agreeing at the sub-centimeter level in terms of consistency in small areas. And so we're kind of happy, we're very happy with that. What that allows us to then do is come out with a distributed deformation map on the right here. So you can see what's on the left and what's on the right. And one of the first things you'll notice, this red line here is actually the official USGS fault line. Well, you'll notice over in this neighborhood here, it's actually not on the fault. At some location here, the fault actually jumps over to another fault location. The way the USGS maps this is they just go out and they look for where the pavement is cracking. But there's no guarantee the pavement's always going to crack right on top of the fault line. So it really shows that it's just an approximation of where the problem is. So I think I'm kind of running out of time here, so I'll just kind of jump a little bit forward. Because this is an area that's moving really slowly, we can actually compare ourselves to the UAV methods because they are able to track kind of centimeter level displacement. So over in this figure here, you can see the blue dots are the estimates of the fault creep with MLS, and the gray in behind is the UAV SAR estimates. What's really important to note here is we are actually getting a measurement of that curvature right at the fault. And this is the really key point to this method is we can actually start to measure that curvature, which tells us what is happening below the surface. So the fact that this line is curved tells us that at this station, all of the energy from the fault movement is not actually making it to the surface. There is a zone where the energy is being absorbed at a distance of probably 2 to 4 kilometers below the surface. Why is that important? Well, if this was a straight line, that would tell you that the whole fault is moving and there's no energy being stored up in it. But the fact that we see this bending tells us that there's a bigger hazard along this fault because there is energy being stored at depth. And so that's a really important earthquake parameter from this. But of course, geomatics crowd, we don't care about that. You just want to know, well, how accurate are your measurements? So this is going and looking at those theodolite alignment array sites and comparing those to the displacement that we have estimated using the MLS. And so you can see these are the MLS display or the alignment array displacements, and this is the MLS estimate underneath. And we're agreeing at a level of about 7 centimeters, 1 sigma for these measurements, and it's within the accuracy level of the alignment array observation. So this is just one result, but at several sites we're kind of down at this sub-centimeter. So constraining the geometry to these planar surfaces adds significant observational, or reduces significantly the observational noise down to a level that's an order of magnitude better than what we were getting with ICP. The other important thing to note here is that you'll notice that these 2 points are not on the edge of the fault displacement. The places where it kind of flattens out are more than 150 meters away. What this says is that the USGS is actually underestimating how much the ground is actually moving in this location. And again, that is another important result because it shows them that they are underestimating the hazard along this because they're underestimating how much it moves. So conclusions from that study. And again, this is published in the ISPRS journal, but we're getting kind of centimeter level change with sub-centimeter level accuracy. We're able to measure the distribution offsite and actually get at that curvature. Very briefly, the next piece of this that hasn't been published yet, but that is part of Sean's dissertation is, well, that's just deformation between 2 epochs, 2017 minus 2015. But I mentioned we've been observing this for 8 years. Well, what is often done in INSAR processing is you stack a whole bunch of interferograms because as you keep stacking, you reduce some of the atmospheric noise. And so we started thinking about, well, can we stack things here to do a Lidar time series? And the answer is, yeah, you can actually add an additional constraint to the data set that considers a time-wise change. So in this next slide here, just a little cartoon to kind of discuss this. But if we have measurements from 2015, 2017, and 2018, for example, we can measure the displacement from 2015 to 2017 and 2017 to 2018. But when we add those 2 together, they should be the same as an independent displacement from 2015 to 18. And so we can take our least squares solution that had our geometry constraint and actually add another constraint that is the shared displacement. And that constraint is that the dx, dy, dz from 15 to 17 plus from 17 to 18 plus and you notice here we've reversed the years 2018 back to 2015. If we add those three together, the answer should be 0. And so we're adding a third additional or another additional constraint on. And if, this is only looking at 2 epochs, if we had more epochs, we could actually add additional constraint equations to this. But for simplicity, I just added 1 here. And so Sean's work is then using that to basically automatically determine all of these displacements in one combined least squares adjustment. And what comes out of that is that we are actually able to determine the displacements compared to these alignment array markers with a little bit better accuracy than if we just look at 1 epoch. And we're not talking an order of magnitude better here. We're kind of going from like 7 millimeters down to like 4 or 5 millimeters. So it improves the results a little bit, but we're really starting to get down to the noise level of all of the observations here. So conclusions of the study, we can resolve multi-temporal change by stacking several of these together. We are able to detect at, again, a sub-centimeter level. And more importantly, we're able to measure the off-fault deformation at both high accuracy and high resolution. Where's this going next? Well, we're going to add some additional time series. We're going to keep comparing with the UAV star observations especially. And where the USGS is going to take this next is actually use those observations to do a shallow fault inversion to really understand what is happening in the shallow fault region of the Hayward fault. So thanks for your time. I think a couple minutes over. I apologize about that, Jinha, but anyone's interested in discussing this a little bit further or has a question about getting some Lidar data for one of their projects or anything like that, please feel free to email me, clglennie@uh.edu. If you want a little bit more details about the National Center, you can get them at the ncom.civ.uh.edu. So thanks for your attention, and I'm happy to answer any questions that you might have.
Thank you very much for your presentation. I really enjoyed it. And this is something that, here Purdue Geomatics has not been studying at all. So this is a, very good example of how this geomatics engineering is going to be influential for some of the other areas of, discipline. I think in that regard, I think it is very refreshing and I enjoyed your presentation a lot. So if you guys from the audience have any questions, please feel free to unmute your microphone and ask the question, or feel free to type in your question in the chat window as well. While you guys are working on this, probably I'm going to start with a question from my side. So in one of your presentation, you showed the geographic distribution of project that you've been working on as an ANCOM. I see that most of focus is on West Coast and very little on Midwest. I'm gonna say it is because mainly you've been focusing on earth science related topic as a main focus area.
Yeah, I mean that's just, I'm trying to get back to that slide here. With me. It is mostly because nothing exciting geomorphologically happens in Kansas. Where the important stuff is, is kind of along the continental boundaries. Snow in the Sierra Nevadas, deformation along the San Andreas Fault, and so that is really the driver behind it. The other driver is, for whatever reason, especially recently, there's a lot of kind of lower resolution Lidar data for some of the states from the USGS 3DEP program.
Yep.
And so that has driven a little bit. Yeah, so this slide here, I think, right?
Yep.
So yeah, I mean, and if you looked at the distribution, most of the projects are over in this area here. Mm-hmm. Most of the stuff in Central and South America, this is all archaeological projects because, the Mayan subculture kind of fits in a circle about like this. Is really the area of study for that. It's not that we don't want to fly in Kansas or Oklahoma. It's just that no one has come up with any good NSF projects there.
I know that one of our students submitted a recent research proposal to an ANCOM. So hopefully, you guys are considering that one as another project, so that we can have another state mark in this map for the future.
So I don't actually review them. We have an independent board of faculty members that reviews and concludes. And so we've actually done our awards for this year, and I don't remember.
Okay,
when
probably
Purdue,
didn't make
so,
it then.
Yeah,
But that's fine. We'll give it a try next year then.
for sure.
Yeah, and I remember that I think you also mentioned that you are also doing a lot of archaeological related research. I think I remember seeing some of the article from like an NPR or something where you guys collaborate with somebody who is looking for lost cities in Central America. He
Yes.
spent tens of years trying to find it. He couldn't find it, but the ANCOM just flew down there and collected Lidar data. He just found it immediately. So you want to share that story?
There's a National Geographic special
Yep.
on it. There's actually a documentary, and there's a New York Times bestseller on that project.
Yeah.
It's called the book is called Lost City of the Monkey God.
Yeah.
So if you want to look at it, it's a pretty good book. No pictures of me, so you don't have to look at my face. Good book.
So were you involved in that project as well?
Yeah, I mean, for sure that the center was involved. Primarily our field research associates, of course, went down and collected and processed the data, and so you'll see them mentioned quite predominantly in there. I will say, Jinha, if maybe not for this semester because it's almost the end, but if you're interested in a really good LiDAR archaeological talk, you should really invite my co-PI Juan Fernandez Diaz to give one. I've seen his talk and it's fantastic.
I mean,
I'll email you. I'll introduce you
yeah.
by email after this.
Appreciate it.
But I think your students would really enjoy his talk.
Yep.
Not only does he do that, but he also goes into the field to verify these sites afterwards. So, it's kind of cool, some of the pictures he has from these sites that he's gone into after we've discovered them from there.
That sounds good. So any question from the audience? Please don't shy. Dr. Shen, please go ahead.
Hey, Craig, good to see you here.
Thanks.
It's a wonderful talk. So I had hoped that we have some faculty from Earth Atmospheric Science at Purdue could join your talk. And maybe next time when Jinha invite your colleague, and we should reach out to the other departments. I think we are right out of time, but I have a very quick question about the deformation, and you mentioned it many times. So what underlying assumption do you assume? There's seems that many of the models you are using is kind of a rigid transform. So do you assume this there's only one displacement or similarity transform there, or do you accept non-rigid deformation in general?
So what we are currently doing is in a very small region. So, the region where we have 12 planes, we assume that all 12 of those planes have deformed in the same manner. But if you move 10 meters over to the side, you can have a different transformation. So it's kind of blockwise rigid. So you have varying, but you make a small assumption. There is some work from one of my other students that uses a approach called coherent point drift that is actually relaxes to a non-rigid. Unfortunately, the math is very nonlinear and hard to get to converge in a number of these situations. So we're still working on getting a reliable solution out of it. But if I go look back and look at them,
is that because you transformed to the parameter space instead of feature space, instead of you stay in Euclidean space?
That's right. And so the coherent point drift stays in feature space and models everything. You know, it models everything as a Gaussian process, basically. And so you can then get a nonlinear model for a displacement. However, you know, even if we were able to do that, the shallow fault physics models to do their inversion below couldn't accommodate them anyways. They're such nonlinear problems that they can only use a couple of thousand observations before their inversions become improperly posed and they can't actually invert them anymore.
Yeah, I think but even though if you follow the idea of piecewise kind of rigid or solve your problem, kind of piecewise restrict your problem or divide and currently divide into many small parts that may need some conditions, right, between different parts, and that may still stabilize your ill-posed problem.
Yeah, for sure.
What kind of condition will be introduced between different parts?
The ideal would be to condition the observations based on the shallow fault physics model.
Mm-hmm.
The last thing we want to do is condition our observations on themselves, because that actually could change the conclusion that you get from the inversion. And that's probably where we will have to eventually go. You know, assuming the USGS continues to decide that this is interesting work for them.
Yeah, I would assume that you are not doing this just by using Lidar data, you know, whatever tool that you collect the Lidar. There must be some permanent stations that you can fit your work into the permanent stations. So
so right now, we are measuring against a few permanent stations, but the problem with the permanent stations is they only give one observation, and you can't get a profile with one observation, right?
I mean, you need two. So
yeah.
But the other one is even for the small building that you showed me showed us on some of the slide. But you still assume the plane is deformed to a plane. So basically, these are shifts, right? But when you are talking about centimeter level, and that, I mean, the plane, because of an earthquake, so they may not be linear anymore at the sub-centimeter level. So
yeah, so I kind of glossed over that, but we qualify the planes a little bit on the front end by, you know, if they are not nice and flat surfaces, we don't consider them for the least squares adjustment. So I'm trying to see if this is actually a nice house, most of the points, but you can see there's a lot of points that are not included in the model, and that's because we've looked at that and said, it's not planar enough for what we want.
Okay, so the question is that, are you solving the parameters plane by plane without any connections or conditions, or you solve the parameter, one set of parameters for all the planes?
No, each plane is has an individual, well, each pair of planes, right? We assume this plane, this garage door and this garage door are the same plane. And so we would solve, but each different color here would have a different set of plane parameters.
So that might be more reasonable if you introduce the constraints between the parameters on different planes, right? You assume the shift should be somehow at least very close. So that means that may solve also under certain, you know, extent, consider the non-rigid transform.
Mm-hmm. Excuse me.
So anyway, I think I don't want to run too much over the time, but I think I wanted to talk to you, maybe Jinha wants to be involved too, about the operation of your center. That's something that's quite interesting to me. And maybe I can schedule another time.
Yeah,
Sure.
Craig, if you don't mind. So.
of course not. Just Jinha, or just send me
Sure.
some times that work for you guys, and I'll pick one that works for me. And
Yeah,
we can
the
get back on Zoom.
administration and the operation. I think our Earth department and me have some collaboration with you. So.
I know that the Purdue has a pretty big group doing earthquake-related research as well. So.
Mhm.
The good thing or the bad thing is that we don't have much earthquake here.
Well, yeah, I think that's a good thing.
Yeah. I mean, Houston doesn't
Well,
have an earthquake neither, I guess.
So it's funny, we don't have earthquakes here, but we actually have lots of fault lines.
Oh, really?
It's just that they don't store energy.
Okay.
So there actually are things that there are fault lines here that we track with laser scanning too.
Okay.
Okay, anyway, thank you. I don't want to hold you too long, so thank you.
But no, nice talking to you. Thanks.
I know we are over time, but if any of student has a question to Dr. Glennie, by any sense? Silence. It means that.
All right, I must have explained it perfectly, Jinha.
No, I mean, I really enjoyed your presentation. I recorded this and I'm going to make it available, for everybody who were not able to make it today. So I'm pretty sure, they will, enjoy this recording as well. So thank you
Sounds good.
again very much for your time, Dr. Glennie, and I really appreciate you coming and give us a seminar. And thank you very much.
Okay, talk to you soon. Thanks.
Okay,
Bye
bye-bye.
all.
Mhm.